Now, you have to notice one thing. If the data actually do not really fit a straight line and still you apply this method, you will still get some value of m and some value of b, and that does not mean it will make any sense. So, one has to first ascertain that either from the theory you do expect a straight line fit, or the data when plotted do indicate a straight line fit, and then only you should apply this method to obtain the values of m and b. Else what you do, I will come to that later, where the curve, the graph does not indicate a straight line fit. What do you do then? I will come to that later. But obtaining what you have just obtained, that means we have obtained the value y is equal to mx plus b, we have obtained this and we have obtained this. This does not suffice. The reason is that we have obtained some values, but whenever we want to state it, we always have to state with the error bar. So, we have obtained the estimated value of m, but there has to be an error bar stated with m, there has to be an error bar stated with b. So, from the data we have to also obtain the standard error in m and the standard error in b. Without that, the scientific enterprise of estimating the straight line fit is not complete. So, in order to do that, first let us try to figure out how much would be the deviations. That means, the delta y I, these are the deviations of the actual data points from the straight line fit, right. So, these are the deviations, and if these have a distribution, then there should be a mean and there should be a standard deviation, right. How do you calculate the standard deviation of this? How do you calculate the standard deviation of the deviation from the straight line fit? That means, while we do that, we are assuming that we have estimated m and b, thus we have estimated the straight line, and now we are talking about the deviation from that. So, I will write it as s square, which is the variance of delta y. What is that? That will be all the various delta y squares, but now normally in order to obtain the variance, we divide it by n total number of points minus 1. But here notice the points are not scattered in any possible way. The points are scattered around a one dimensional object. It is basically these deviations we are talking about, not just a scatter of points and their standard deviation. So, because it is now scattered around a one dimensional object, therefore the dimension has reduced by another 1. So, it is minus 1, another minus 1. So, effectively it is n minus 2. So, this is how you have to obtain the standard deviation after you have obtained the m and b, so that you have estimated the straight line, then, because then these are calculated from that. So, we have calculated the standard error, standard deviations, square root of that will be standard deviation. Now, we are actually trying to find out the standard deviation in m and the standard deviation in b. What does that depend on? They depend on these deviations. Okay. So, they depend on this deviation. Now, what we will do is that earlier when we were talking about a variable z depending on x and y, we knew the error, standard errors in x, we knew the standard errors in y, then what will be the standard error in z? So, we had earlier encountered a situation where z was a function of x and y. Then we saw that the variance in z is the derivative of z with respect to x square sx square plus derivative of z with respect to y, with respect to y square sy square. So, this is something that we encountered earlier when we are talking about propagation of errors, and this is what we will use. In what sense? In the sense that the deviation, the variance in M, the variance in B will be dependent on the variance of these y's, delta y's. So, that is how we will use it, and let me, if I want to write it, it will look something like this. The variance in M will then be dependent on delta M by delta y1. y1 is actually the first point, say here. The delta y1 that means the difference of the first point from the straight line. So, delta y1 times the variance in y1 plus delta M delta y2 square times the variance in y2 plus dot 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 dot. Why? Because, let me write it, since M is a function of y1, y2 and all that, those data points. Because of that, now the variance of y1 and y2 and y3, these are not actually different things. These are basically this variance. So, we can simplify that as delta M delta y1 times this one is nothing but s square delta y plus, because this is delta y is generally the s square delta y is the variance of the data points from the straight line fit, and this is just one of them. So, it will have the same character. Similarly, delta M delta y2 times s square delta y plus and all that. So, effectively then this will get the s square delta y square common, and what remains inside is nothing but the so these are all squares, sorry, these are all squares, yeah. Basically it is these individual ones, so which can be written as sum over delta M delta y k its square. So, I will have to put here square, okay, and sum over k. So, all I have done is to take these common, what remains are these terms, I have expressed that as a sum, that is what I have done. So, now now we need to find out these values, okay. So, in order to find these values, I will use whatever we had earlier calculated as the M and B, I will use, but let me erase this because we need space here. So, Sm square, the variance in M is given by this, and now we have already seen M was what I just erased. I'll express that as two separate quantities. The denominator first, that was n sum over xi square minus sum over xi whole square. That was the denominator. The numerator was n x1 y1 x. The I am breaking apart in form of 1, 2 and all that. So, it will be n x1 y1 minus, it was y1 sum over xi. So, that was the first term. Similarly, there will be similar terms for 2. So, plus n x2 y2 minus y2 sum over xi dot 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 and that continues. Okay. So, now we are to find the derivatives. So, we have to differentiate m with respect to delta y1, okay, the first one, and that will indicate what will happen for the general case k. So, if I take the derivative, the denominator remains the same. So, denominator is n sum xi square minus sigma xi whole square. Now, this one yields first one is only n x1, this one is sum over minus sum over xi, and that is it, because the rest will disappear. So, similarly for y2 it will have the similar terms, only 2 here. Similarly for yk it will be k here. So, we can, in general we can write the delta m delta y in general, the kth term is, the denominator remains the same, n sum over xi square minus xi whole square. Here it will be n x sub k minus xi. So, in general we can write this, and if we can write this, then we can also write its square. That is what we need ultimately, because we are interested in the terms like this which have a square. So, delta m delta y k, its square will be this term squared is equal to 1 by this term squared, this whole term squared. In the numerator it will be, let me write here, n square x k square plus sigma xi whole square minus twice n x k sigma xi, right. Okay. Now, we have to, then what we need is a sum over all k, right. This has to be summed over all k. So, we need to sum this over all k. So, sum over k of this fellow delta m delta y k whole square. So, this term, the denominator did not contain any k term, so that will remain as it is. So, I will just write 1 by whatever it was square. I am not writing every time because it will only consume time. And here we have sum over k of this term. Okay. So, let me just write n square x k square plus sum over xi whole square minus twice n x k sum over xi. This is what we have to calculate. Now, notice that the sum over k x k is same as sum over I xi, right, because this I and k, these are just dummy variables. So we can proceed as by expressing this as, this can be now written as equal to, I'll keep the denominator as it is, 1 by this square. In the numerator, this will become sum over, I'll change k to I, it is n square, it would be sum over xi square. This one is repeated n times, so you will have n plus n sum over xi, this is whole square minus twice n, this one will be, this one xk sum over this will result in the same as sum over xi. So this will be sum over xi whole square, because this sum over k xk and sum over I xi are the same things. So this is basically sum over I xi twice, so it has become square, is equal to again 1 by whatever it was in the denominator square. Now notice that this and that are the same, this is only twice of that, so we get simply n square sum over xi square minus again n whole sum over xi whole square, right. Now notice what was here, you can now take n common, let me take n common, so this one disappears, square is not necessary, this is not necessary, okay, and this one is also appearing, okay, so let it remain as it is, let it remain as it is. So you have this, what was in this bracket, if you notice that it was this, so now let me write it, n sigma xi square, n sigma xi square minus sigma xi whole square, minus xi whole square. Now notice that this is exactly the same, and here is a square, so this will cancel off with the square, leading to a simpler expression, n divided by n epsilon xi square minus xi whole square. So this is what in the left hand side it was this, right. So let me, so that we don't forget, let me write this as sum over k, it is delta m delta yk whole square was this, okay. And you notice that when we wanted to obtain this was what we have been able to calculate, right. So we can now express Sm, the standard deviation in m, as standard deviation in delta y, which we have already calculated, times the square root of this, square root of n by n sum over xi square minus xi whole square. So, this is the standard deviation in m, and in quite the similar way we can calculate the standard deviation over b. The method is the same, but it will again be a repetition of the same method of calculation. So, we will not do that, we will simply write the result. It is again the square root of n, not n, it will be in this case sum over xi square divided by the same thing, n sigma xi square minus sigma xi whole square. So, we have been able then to obtain the value of m with an error bar, and the value of b with an error bar. The value of m with an error bar, value of b with an error bar, m and p. This is what is needed. That means, when we talk about a curve fitting or a straight line fitting, we essentially estimate the values of m and b, but at the same time we have to estimate what could be the error, what could be the standard error of the mean for these, for m and b, and this is what we have been able to calculate by calculating the standard deviation of Sm of m and b. Standard deviation is Sm, standard deviation is Sb. This was where we were trying to fit into a straight line, but as I said, all fitting need not be fit into a straight line. There are other situations where some non-linear fit is necessary, but in that we have to be a bit careful, because there are certain non-linear functions that are more prevalent, common in physical sciences, and there are some which do not really yield much insight. The ones that are really important are the exponential function and the power law. So, first the power law, and second the exponential. These two functional forms yield to some physical insight, and that is why physicists are often interested in this. For power law, it is y is equal to x to the power some constant a, and this is y is equal to e to the power x, or let me write a rather general form. One can write it as e to the power some mx, and there is a coefficient a. That is a general form of the exponential function. How do you do that? We do that, we extract these by actually reducing to the linear form. How? If you plot that in a log graph, then you actually do this, a log of y is equal to a will come to the front, a log of x. So, this is a straight line relationship between two logs, and the log could be log of anything, I mean with the base of anything. It could be 10, it could be 2, it could be e, whatever. So, in this case we simply plot the same data on a log graph, and if it now approximates a straight line, then it is a power law, and the straight line fit can be found exactly the way I have just shown. In case of the exponential graph, we plot it on a semi-log graph, where this will be in ln and this will be just plotted. So, this will be ln y is equal to, this will be ln a plus this will be just mx. Now, because it is e to the power mx, this has to be only to the natural logarithm. This will be in the natural logarithm form, and if you do that, then you will get again a straight line fit with this representing our B, whatever we have calculated earlier. So, in both these cases, it can be cast in the form of a straight line fit, and the straight line fit can be obtained by the least square method that I have just shown. So, all these forms then that can be extracted from the same method that I have already illustrated. If there is some data which cannot be cast into either of these forms, but it is apparent that it is a nonlinear data, then we try to express it as a polynomial fit. Polynomial fit, which is basically y is equal to say some a0 plus a1x plus a2x square plus dot dot dot. This any graph can be fit into this form, but let me tell you that it does not really yield any physical insight. Having expressed a graph in this form is essentially admission to the fact that you are saying I do not know what the functional form is. So, this will not help the theorist to obtain a reason why it should be so. If it is a form like this, then a theorist can try to find out why it should be so. If it is like this, then also the physicist can try to find out why it should be so, but if it is like this, one cannot. So, in general, even though any graph can be fit into the polynomial form, it does not really lead to much insight, and therefore, we normally do not do it. So, effectively meaningful curve fitting are obtained in the form of the linear fit or the power law fit or the exponential fit. The others really do not yield much insight, and therefore, I will not cover that in this course. Let me end today.